Okay. For section 4.1 for advanced algebra trig, we had a huge lesson today. It's 10 boxes, okay? The first idea here of okay, so my definition of what I gave to everybody today was you take some stuff, right? You do something to that stuff, and you get other stuff. Now, that's not like a precise definition, but it makes sense a little bit later on. Okay, the book's definition of a function is this right here. Let x and y be two non-empty sets. A function is a relation that associates each x with a unique y. Now, the key word in this definition is the word relation, okay? And a relation is simply an ordered pair, such as x comma y, or in function notation, x comma f of x. So that's what that is. All right. So there's this idea of what a function is and then what's a relation. Okay. Then we talked about the domain of a function. We had this sort of debate in class. But the first one was we have this set of numbers. Right? We have a as example A. We've got a set of 1 comma 4, 2 comma 5, 3 comma 6, and 4 comma 7. Well, the input values are the first ones, the domains, right? The 1, the 2, the 3, and the 4. So we wrote them down, 1, 2, 3, 4 over here. The output values are the 4, the 5, the 6, and the 7, and we wrote those down over there. And then we mapped each input to its output. So each relation, so 1 gets mapped to 4, 2 gets mapped to 5, so the input is 3, the output is 6, the input is 4, the output is 7. And every single input has a unique output. Therefore, the answer was yes, this is a function. Okay. Then we went on to part B. Part B was where we had the big giant debate. We said, okay, same process. 1, 2, 3, and 6 are all the inputs. 4, 4, 5, and 10 are all the outputs. And so we said, okay, well, 1 gets mapped to 4, 2 gets mapped to 4, 3 gets mapped to 5, and 6 gets mapped to 10. Of course, everybody was wondering, what is the deal over here? Right? Is that or is that not a function? And it turns out that the answer is yes, it is a function, because for every input, there is a unique output. Not unique that the number is the same, unique in that it can be mapped, right? So 1 gets mapped to 4, no problem. 2 gets mapped to 4. I know exactly what the output will be. There's no discretion about that. However, if you go on to part C, you can clearly see that negative 3 goes to 9, negative 2 to 4, 0, 0, 1, 1, and negative 3, 8. Well, the negative 3 has two different outputs. These are not unique. 8 and 9 are different for one single input of the negative 3. That is not a function. Okay, then we went on to talk about how to read a function. So when we see this, it's read f of x, and we see this g parenthesis x is read g of x. Okay, we also spoke about independent versus dependent variables, right? For a given function y equals f of x, y is the dependent variable, x is the independent. So x is independent of y. Y depends on x. Okay. Then we had some fun with this thing. So let me give you an example of these. So I'll erase this and put this up. So I can do that. Put that down. So I'll get rid of this for just a second so you guys can see what we did. Okay, so we had finding the value of a function. The function was f of x equals 2x minus 5. So f of 1, when we look in the computer, it gives us 7, right? So what is it doing? It's taking 1, plugging it in for 2. So 2 times 1 is 2, and 2 plus 5 is 7. So f of 2 should be 2 times 2 is 4, plus 5 is 9. So if I do that, we get 9. Now this one says the opposite of f of negative 3. So take negative 3, plug it in. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1. So the opposite of negative 1 is 1. So this should be 1. And there it is there. So I'll go ahead and finish these up. That one's 5. The opposite of that one's negative 25. And then for a, we just get 2a plus 5. So that's how you find the value for a given function. Then we went up to talk about the domain. Okay, so domain of a function. For right now, we're kind of restricting it to anything that we cannot plug into to divide by 0 or give us a negative in the square root. So for part A, we've got a polynomial, right? Oh, let me get rid of this. So this is a polynomial. And any polynomial function will have a domain of all real numbers. So any polynomial you can think of will have a domain of all real numbers. It's kind of nice. Rational functions, however, we have to be careful not to divide by 0 on the bottom here. So we have to ask ourselves, are there any two numbers that would give us a 0 on the bottom if we plug them in for x? And those happen to be 2 and negative 2. Right? They're bad. Why? Because we'd be dividing by 0, which is also bad. So therefore, the domain is all real numbers x such that x is not plus or minus 2. And then the last one here, the square root of 4 minus 3x. Well, we came to the conclusion that we just want the stuff underneath the square root to be bigger than 0. So that's what we did. We set the stuff under the square root to be bigger than 0 or equal to 0. Solve for it, and we get this inequality here, right? This inequality here that says x must be less than or equal to 4/3. So therefore, we dump that inequality into a domain statement, and we have our domain, all real numbers x, such that x is less than 4/3. So anything smaller than 4/3 will guarantee that you do not have a 0, or guarantee you not have a negative number underneath the radical. Sorry. Okay. Then we talked about the vertical line test, the vertical line test theorem. What it does for you is it determines if a graph represents a function or not, simply just by looking at it, right? And how it does that is by passing a vertical line test. So if you were to run a vertical line over all of these, right, you would see that at any point that line only crosses the graph one time. There's only one point represented by every single vertical line. So therefore, this function, this graph does represent a function because it passes the vertical line test. Okay. Then we went on to graphs over here. And we asked ourselves, okay, which of the following pass the vertical line test and therefore are functions, right? So this one passes, so this is a function, so yes. Since it passes the vertical line test, that's a function. This one's also yes, since it passes the vertical line test. However, these two are no. It does not pass the vertical line test because you can see right here, if I were to draw a line right there, it hits there and there at the same time, so it's not a function. And the same thing over here, right? If I was going to draw a line there, this does not represent the function, so this is not a function either. It does not pass the vertical line test. Not a function. Okay. Then we went on to a conceptual problem for the last thing here. Okay, so to consider this following function, f of x is x over x plus 2. It's a rational function. Okay, we talked about the domain. The domain is all real numbers x such that x is not equal to negative 2. Since a negative 2 placed in the bottom will give me a 0, so we can't have that. Then we ask the question, okay, is 1 comma 1/2 on the graph, and then how can you tell? Well, most people are looking over here. When x is 1, we're trying to see, is that 1/2 or not? When we should just be plugging it into this. Well, what is f of 1? Well, it's just 1 divided by 1 plus 2, which is 1/3. So therefore, 1 comma 1/3 is on the graph. 1 comma 1/2 is not. So the input is 1, the output is 1/3, and that makes sense. If the input is 1 over here, the output right here is about 1/3. So if I got the pen, the output here is 1/3, so that's about 1/3 right there. So when x is equal to 1, the output is 1/3. Then we went on to further explore this. Okay, so if x is negative 1, what is f of x? What's the point on the graph, right? So if x is negative 1, then the output is also negative 1. So this is the point, negative 1 comma negative 1. And you can also get that by plugging in negative 1 all over negative 1 plus 2, negative 1 over 1, which is negative 1. So if x is negative 1, the point on the graph is negative 1 here as well. And then the last one was, what if f of x is 2, right? So notice that this one is asking you when f of x is 2. So we're talking about the function. So when does the function have a value of 2? Well, it has a value of 2 when x is negative 4. So for this answer, what is x? The answer is x must be negative 4. And you can also see the algebra of... Okay. Anyway, so at the very end here, there is a really good summary on page 241 in the book, so make sure that you read that.